Hi, chemistry students. Today we're going to take a look at energy, the second half of our unit, and you'll see that this is in chapter 17 in your textbook. We're going to take a look through that too, the online version today. Here are our big questions. The first one, specific heat capacity and density of water. Why water? Because it's the most awesome compound on the planet. 70% of the surface is water. You should already know the numerical value for density, so today we're going to learn specific heat capacity. Next, I'd like you to know the relationship between matter and energy, and this will show up in the form of an equation, which if some of you think kind of hard, may be able to know, or may be able to say what that equation is. Next, we are going to learn several quantities and units that are abbreviated with the letter C, either lowercase or capital. We're also going to learn some other quantities and units that start with the letter C that don't have an abbreviation of C. Very interesting. Got to keep it all straight. Next, I'd like you to understand the difference between energy and power. And the fifth question of the day is to distinguish among many quantities that people often confuse or interchange. You'll notice that I underlined heat capacity because that is missing from your notes. So we want to distinguish among energy, heat capacity, specific heat capacity, enthalpy, and temperature. All right, it's always great to start with a definition of what energy is, and that is the ability to do work. Next, we would like to know the units for energy. We have our nice English units up here. We have the calorie. We have two versions of the calorie. The big calorie, why am I calling it the big calorie? Because it starts with capital C, and the little calorie, because it starts with lowercase c. Please note that although calorie starts with the letter C, its abbreviation is not just C. It's actually three letters, CAL, either capital or lowercase. The relationship amongst these three English units is down here. 1 big cal equals 1 kilocalorie. And hopefully you remember from your metric system knowledge that kilo means 1,000. So here is our nice little relationship. Big cow equals a little cow. And when you speak, it is nice to tell the person, you know, big cow versus little cow, because they won't have any other idea if you just say, I have, you know, I'm working with 55 calories, because my question would be, well, what kind of calories? When you look at labels for food nutrition labels, the unit that is expressed on those is the big calorie. All right, let's talk about our metric units. We have two of them, the awesome joule and the electron volt. Joule is a larger unit and the electron volt is smaller, and that might make sense to you because hopefully you know the electron to be a very tiny particle in an atom. So it makes sense that if we're using electron volts in terms of energy, that's going to be very, very small energies. Also a reference for your brain for about a joule, what a joule is. What's it kind of look like? Imagine your favorite food, lasagna, pizza, cheeseburgers, garden patty. It's on a plate. You're either going to grab that piece of food with your hand, or you're going to put a piece of this food on a fork or a spoon, and you're going to lift it to your mouth. The amount of energy that you exert to lift that food from the plate to your mouth is about a joule. And final thing, how do we measure energy? Well, we measure energy with a tool called a calorimeter. Not the best name for it. It doesn't literally mean measures calories. So if we want to, you know, break this word up here, meter is something that means to measure, and it does not mean to measure calories. It means to measure what calories are the unit for, which is energy. So if you want to jot down here a little definition, it is an instrument that measures energy. Whee! All right. You have better handwriting than me, I am sure. Okay. First quantity that we're going to look at here, besides energy, would be something called specific heat capacity. It is another quantity that's good to reference when you're talking about substances, and we like to focus on water. Notice the abbreviation. Capital C is the abbreviation. And I'm going to put a little SP down here for specific. So this C is usually capitalized. I've seen it both ways, and it's not designed to confuse you. It's just, this is a weird quantity. You may also just hear it referred to as specific heat. I've seen that. I always like to focus on the word capacity because it helps me remember that specific heat capacity is abbreviated C, and then I put a little SP for the specific, and then I put the substance. What do I want to know the specific heat capacity of? Okay, let's read the definition. This sounds really crazy. It's not that bad. The amount of heat, which can be abbreviated lowercase q or capital Q, in little calories or joules, that a mass of 1 gram requires to change its temperature 1 degree Celsius. You may notice this symbol and it may look familiar to you. We saw this before with boiling point elevation. It is the Greek letter delta, and it means change in. So change in temperature. So before we take a look at the formula and the units, let me just put this in a context of something that makes sense to you. You understand the word capacity. It's an ability to hold. So this is a substance's ability to hold heat, and we make it specific by saying how much of that substance we have, because it's going to influence the amount of heat that can hold. Think about when you boil water on the stove, when you're making your awesome macaroni and cheese. The pan and the water both will heat up very, very hot. And then if you were to pour that water into another container and leave the pan sit off, one of those substances, and let's pretend your pan is made of steel or aluminum, one of the substances, either the aluminum, steel pan, or the water, is going to cool down a lot faster. And the reason that is because of the specific heat capacity. Water will cool down much slower than most metals, and this is because water has what's considered to be a high specific heat capacity. It holds on to heat very, very well, whereas metals don't. Heat flows through them very effectively, but it does not, metals don't hold on to it. So when we look down here, I just took that definition and made a little fraction of the key quantities. We have the quantity of heat divided by mass times a temperature change. When you look at this in terms of symbols, how do you abbreviate specific heat? Capital C, or as I set up here, you can put a little SP in the substance and make it a little bit more elaborate. The symbol for heat is typically lowercase q. I've seen it uppercase though. The symbol for mass is M, and temperature change is delta T. Now when we look in terms of units, specific heat capacity is going to have 3 units because it has 3 quantities that make it up. You can either use the English unit or the metric unit, joule, and then both of these are metric unit, grams for mass, and degrees C for Celsius. Okay, if you haven't opened up your online textbook, let's do that together right now. I want to check out chapter 17. Oh, and also, if you didn't know that you can search by page on the online textbook, that's really a cool thing to do. So my login's all ready to go. And you guys remember it's worldwideweb.pearsonsuccessnet.com. Your screen looks a little different than mine, but here is our textbook, and I want to go to page 508 because that's what Miss Miller said to do. Click go. Here we are. This looks like something we were just talking about. A little bit of description. Oh, and voila. Here is this specific heats of common substances that Miss Miller just was talking about. Okay, so notice there's 2 columns for 2 units, and we have a variety of substances: water, alcohol, ice, mercury, silver, iron, aluminum, etc. All right, so what do we notice? Well, 1 for what substance? Water. Be very careful that you use the right unit though. So you can tell me that the specific heat of water is 1 as long as you pair it with calorie per gram degree Celsius. If you use joules, the number is slightly larger. When you evaluate this table, you will see, as I mentioned in my cooking example, water has an extremely high specific heat capacity when you look at it compared to other substances. It can really hold on to heat very, very well. All right, so let's see. Why don't you guys take a minute and write in your own words what specific heat capacity means based on what I just said, and answer the question, what is specific in specific heat capacity? This would be a good place to pause because I'm going to keep talking. Okay, going on. There's the table we just looked at for your everyday reference. Okay, just a few quantities to go over. Another thing, if you don't have this out, you might want to take it out. Just a couple of things worth having out would be your vocab sheet, just to remind you where these words are coming from. We are progressing through, almost finished. We are going to mention the word endothermic and exothermic. You've already been quizzed on those, and I think you're pretty comfortable with them. We're going to mention temperature today. But a majority of what we are talking about comes from down here. See all this stuff. And then the last page is primarily our energy page. And notice how here I chose to use the heat for capital Q. The abbreviation for heat is capital Q. I mix them up, and I know many other scientists do the same thing. Something else while we're on it to have available is, you may recall this sheet I gave you where we classified matter. You guys wrote in a whole bunch of stuff. If you take that out and check out the back, I've done a little organization for you in terms of several units that we're going to do throughout the year. We mentioned dark matter and ordinary matter, and we've talked about our states here. We've looked at pure and impure substances, mixture types, elements, compounds, and dividing them into metals and nonmetals and metalloids. So we've done this little piece here. We have several more units which we're going to talk about, these pieces here and this piece over here. But now we are venturing over here into ordinary energy, because like matter, it also has a dark form, which is beyond the scope of our class. We're going to classify it and talk about all of these different types. So, fun stuff. All right, these are definitions pretty much straight off of your vocab handout, but I just wanted to take time to go over them again. Heat is referred to as an energy transfer. It is a flow, and it has a single unit, metric unit for joules, and English unit for calories. And we use the little cal in science, not the big cal, even though that's the one that's on your food. And I have no idea why heat is abbreviated Q. There's probably some origin behind that, and maybe one of you can look it up and let me know, because I've never actually looked that up. Okay, enthalpy has an interesting abbreviation. It has nothing to do with E, so it's actually called delta H. Notice we have that awesome delta again. You may want to put a little note here and keep reminding yourself. The more you write it, the easier it gets to remember. Delta. Now, if we remember that delta means change in, we can think of the H as being a change in heat. So that helps out a little bit. And the unit, this one is going to have two units. We're going to have either the non-metric, little cal per gram, or the metric, joule per gram. And finally, temperature. Temperature is simply a measure of hotness or coldness. That's how you define it. You're very familiar with its 3 units. So I think we're pretty good with that one. Okay, heat and enthalpy. This looks a little bizarre when you first look at it, so I want to just take a few moments to explain it to you, because we have already learned the words endo and exothermic. So we already kind of have seen these two words. Now we're actually going to put a symbol with it. We're going to look at endothermic as having positive enthalpy. What does that mean? Oh boy. We have Q with a cis and Q with a sur, and one of them's negative. This is the relationship between systems and surroundings, because if you recall, energy needs to be transferred, and it's transferred in the form of heat. When we do this in reactions in chemistry, we usually want it to be specific for mass, which is why we use enthalpy, because you'll remember that enthalpy is energy change per mass. So this would be your reaction, your system. You have a heat of a system, it's positive, The heat of the surroundings is negative, which means the heat or the energy is leaving the surroundings and going into the system. That is a definition of an endothermic process. The system will warm up. You do not notice this. This is what you, as a scientist or as a student or as an observer, you notice the temperature of the surroundings. So even though this system or this reaction technically warms up because the energy is going into it, you will, if you have a thermometer, notice a decrease in temperature. I can let you pause this for a moment and you walk yourself through the opposite process here. Okay, to relate our two main energy units, the little cow in the English system and the joule in the metric system, we have two conversion factors. And my first question to you is, are these pairs the same? Let's take a look at it. We have joule equals calorie, joule equals calorie. What's different? The numbers relating them. So are they the same? Well, let's think about this in terms of algebra. If you wanted to take 4.184 and get it to be a 1, mathematically, what would you do? You would divide by 4.184. Now, in algebra, you're not allowed to do something to one side and not do it to the other. So we also must divide this by 4.184. When you divide 4.184 by itself, you get 1. Grab a calculator. If you need to pause, do it. Take 1 and divide it by 4.184, and you should see that you get 0.239 calories. So are these two conversion factors the same? Yes, it's just a matter of preference when you look them up, which way it will be printed, but they are exactly the same thing. So then I hope you'll take my word for it that the relationship between the two metric units, remember the little itty bitty electron volt? Look at how many joules it equals. That is 18 zeros to the left here. This is a really incredibly tiny amount of energy. And how would we get this conversion factor? We would divide both sides by 1.602. If you're good with scientific notation, you can go ahead and practice that division and show for yourself that it works. We haven't learned scientific notation. It's one of our upcoming topics. So we'll come back and revisit this. All right, finally, not finally, just to wrap up a discussion and relate energy and power, I want to tell you how they're related to each other. So power is energy per time. So we have another feature we add here. A lot of people confuse energy and power and they think they're the same thing. So power is an amped up version of energy because we put it in with time, and anytime you do that, that's a rate or a speed. Think about when you describe your rate of driving, you call it a speed and you are driving miles per hour, which is distance per time. And a little hint in the metric system, the unit of time, metrically speaking, is usually the little itty bitty second, whereas over here in the States, we usually use the unit of time of hour, which is much larger. So if you literally take energy, its unit is a joule in the metric system, and time is second, power can be expressed as 1 joule per second. However, for convenience sake, we also have another unit, which we call the watt, which you have all heard, because we actually use this in our energy bills. We use something called kilowatt hours to be billed for electric usage. And just to pay a little tribute to the watt, it did not come randomly. It actually came from this dude, James Watt. You can Google him and read all about him. He basically gave us the steam engine, played around with some electricity, so we decided to name an awesome unit after him. In the English system, our awesome American system, horsepower. You have all heard of this. You can Google the origins of that or actually what it means or how big it is, but I do know for a fact that 1 horsepower corresponds to 746 watts. This is a great opportunity for me to tell you a little trick in chemistry for conversion factors. If you have a bigger number, so right here is our bigger number, it must be paired with the smaller unit. So 746 is bigger than 1. Therefore, the watt is the smaller unit. So if I ask you, Which unit is bigger? You do not look at the number to answer this question. You have to look at the unit and you would say, okay, which unit is bigger? 746 is the bigger number, so it must be paired with a smaller unit. The watt is smaller. Think of it another way. You need 746 of them to equal 1 horsepower. So the watt is much, much, much tinier than the horsepower. Quick pause here for a second if you need to pause and think before I tell you the answer. How did we get from that conversion factor to this one? And the answer is we divided both sides by 746. 746 divided by itself turns into 1. Grab a calculator. Take 1 and divide it by 746 and you should get this number. And we already answered this question here. The watt is the bigger unit. All right, awesome progress. Our two main forms of energy. Pause. I think you know this. I know you know this. It just may not be coming to your brain right now. And the answer is, the first type is our awesome kinetic energy. This is considered to be very ordered. You may see it or it may be unseen. If it is unseen, however, you usually will see the results of the movement. So you will see the influence on something you can see. And I like to think of air as a great example. If you think about air, it has an incredible amount of energy from its movement. When you think about hurricanes and tornadoes, the wind can just blow through and totally blow things over and destroy things. So the movement of air can be highly energetic and highly destructive. It can also be very subtle. And if you think about how you smell that awesome pan of lasagna in the kitchen while you're in the living room, or you think about that smell of somebody who sprays perfume on one side of the room and you smell it on the other. How does that smell get to you? It's because the air molecules are moving and allowing that smell to diffuse across the room. Let's take a look here. These are different named forms of kinetic energy. Different scientists will categorize kinetic energies differently. This is the way I do it. We got mechanical, electric, electrochemical, electromagnetic, and sound. You can read through your definitions. Let me just say a few. We have electric showing up 3 times. If you did not know that electricity is it's the movement of electrons through wires, that's what it is. Electrochemical is going to be the movement of ions, which are charged particles, which can be, they can be atoms that are charged, individual atoms, or they can be molecules. They're not electrons, though, generally. Yeah, I guess we can have single electrons there too. Okay, electromagnetic is a movement of a particle we're going to learn a lot about later, photons. And an example of electromagnetic energy is light. You know light. There's about 9 other forms of electromagnetic energy. Microwaves, ultraviolet, that's what UV stands for, and IR. And these all come from the sun. We get some mild microwave radiation and radio waves, background noise, just from outer space. This kind of energy is surrounding us all over. You even give off electromagnetic radiation. You give it off, and we usually just say that you're giving it off in the form of heat, but it does have electromagnetic properties. And finally, we have sound, the invisible movement or compression of air molecules, which results in noise. All of these forms exist in our bodies. Pause this and tell me or pause this and just think where you will find these forms for a moment, because I'm going to go ahead and tell you the answer. So pause now. Okay, so where are you going to find these forms? I hope that you know mechanical is pretty much what you do all the time. Every time you open your mouth to speak, blink your eyes, lift your hand, all of that is general movement. Electric. You have a heart and a brain that rely on electrical impulses to operate. Electrochemical, this is happening as ions move in and out of your cells. We'd already talked about electromagnetic, you give off heat. And sound, you are doing this in your voice box area, compressing air, and it is popping out of your mouth in beautiful sounds. All right, potential energy is our other big form of energy. So generally this is stored energy. That's a really great definition that I think you've heard for probably many years. This energy is also considered to be highly ordered. We break potential energy into two big categories, chemical and nuclear. This would be a great time for us to jot down a little definition. Where do these two stored forms of energy come from? Chemical energy is going to come from bonds. So this energy is going to be in all molecular matter. Molecule means two or more bonded atoms, right? You can have compounds, elements. If it's molecular, if there is a bond there, that substance has chemical energy, and it's named chemical energy, so it's probably one that we really care a lot about in chemistry. We like to focus on reactions, and that boils down to the breaking and forming of bonds. So we're following that energy. Nuclear will not come from molecular matter. This comes from atomic matter. How can energy come from atomic matter? This means single individual atoms, and this is energy that is coming from the nucleus. There are two types of nuclear. Do I go on? Yeah, I go on to that in the next page. Other forms of potential energy could be elastic, pressure, and gravitational. You'll learn much more about all of this in physics next year. Okay, so I had already reviewed with you what chemical energy is. Please note, molecular matter. If you want to draw yourself a cute little picture, you can do that. Happened to my pen, not sure. There we go. Draw yourself a little picture. Energy is here in the amazing box. Okay, nuclear, found in individual atoms. There are two types of nuclear. Fission, which means atom splitting. You take an individual atom, and apply some energy to it, usually in the form of a high-speed neutron, and this will split crazily in half, creating two brand new atoms. These do not have to be the same size. They typically will split highly irregularly. We know this process of fission as radioactive decay, and we live not too far away from a place that is radioactively decaying an element. Do you know what element it is? Uranium! You should check it out on the periodic table. This process also is occurring in the inner core of the Earth. This process generates enormous amounts of energy because there's an energy that holds the nucleus together, and when we bust it, mad amounts of energy are released and the creation of smaller nuclei or smaller atoms result. The opposite energy is fusion. This is not bonding. Totally different. This has nothing to do with a bond. This has to do with, at the essence of the definition of nuclear energy, you take two atoms and they smash together, not bonding, but actually uniting into a single atom. This process also generates enormous amount of energy, and the evidence is Mr. Sunshine. Do you know the elements that comprise the sun? Pause to look at a periodic table and think about this for a moment. Okay, and the answer is the simplest element on the periodic table. If you locate that on the periodic table, you should see that that is hydrogen. The sun is a big, humongous ball of hydrogen gas, hydrogen atoms monotomically existing, and they smash together to form a larger atom, which would be the second largest atom on the periodic table, and that is helium. So where are we going to find helium and hydrogen? On the sun. If you're ever asked this question about, you know, where do you find hydrogen and helium to a great extent in the solar system? It's the sun. We have a lot of it here on Earth, but not in relation to all of the other elements. Hydrogen and helium are considered almost negligible. It's not in the air. We don't breathe hydrogen. It's so minuscule we barely even consider it to be there. All right, heat transfer or energy transfer. This is what we call heat. Some people use heat as a synonym for energy. And most of the time you can, as long as you understand that energy is a little bit more elaborate. It's got different categorizations. Heat is a very disordered form of energy, and it only shows up the instant you talk about transferring energy from one object to another. And there are several ways that this can be done. Radiation is done in the form of waves. So how does the energy from the sun get to us? It is way too far away, 150 million miles, 93 million miles, or 150,000 kilometers. Radiation is heat transfer via electromagnetic waves. Electromagnetic waves. Okay, and if you'll recall, light is a form of electromagnetic radiation. Conduction is touching. When two objects touch, heat will go or move from the object with the high temp to the low temp. You've been experiencing this all your life. This is why you are advised not to touch hot objects, because the heat is going to leave that hot object and fly into your skin, causing an immense burning sensation. And convection is the use of a fluid for heat transfer. Use of a fluid. Great fluids for convection are water. And the other one? Air. Air will heat up and it will start moving, and as it moves, it carries that energy with it. Anytime you convert energy forms, almost every single time, if I want to take, some mechanical energy and convert it into electrical energy, I'm losing energy in the form of heat. It's considered to be a byproduct of just about everything. Heat's everywhere. We're constantly creating heat, which is why the quest for absolute zero or getting ultra cold, or even the act of refrigerating food, is highly energy intensive. It's not natural for things to go the direction of cold. It's more natural for things to go the direction of hot. Okay. And I think we might end here today. No, one more after this. Okay, so law of conservation of energy is the exact same thing as the law of conservation of mass. They're often considered to be combined, and you might hear them both referred to as the combined laws of conservation. You may even hear of it as the first law of thermodynamics. They're all the same. In the word thermodynamic, if you split that in half, you will notice thermo, which means heat. Dynamic, which means changing, moving, etc. Michael Faraday is a new person of interest for us. The only other person we've really spent any time talking about is Lavoisier for mass, so we associate Faraday with energy. He did a lot of electromagnetic experiments. If you want to pause and Google him real quick, we're going to learn a lot more about him. You could just at least see what he looks like. And many people think that matter and energy are unrelated or are different, and this is totally false. They are completely united in such a way that physicists will typically only ever talk about energy. It's like matter is just another form of energy. Do you know the most famous equation in all the land? Yes, you do. Let's see if we agree what the most famous equation is. Einstein's equation, E equals mc squared. So these are all quantities. What do the quantities mean? You jot them down in your notes. I think my handwriting is going to get a little messy here. E is for energy. M is for mass. And C is brand new for us. This is not specific heat capacity. This is not calorie. It is the speed of light. The speed of light is named c, if you would like to jot this down, because it derives from the Latin word celeritas, which means swiftness. The speed of light is incredibly fast. Nothing goes faster. In fact, it's 3 times 10 to the 8th meters per second. This is our rate of travel, distance per time. 300 million meters per second is how fast light travels. Nothing goes faster. So if you look carefully at the equation, you will clearly see that energy and mass are intimately connected. All right, if you are in periods 2, 4, or 7, I have 2 crash course videos that I would like you to watch and jot notes like you did previously. If you are in other periods, you can feel free to watch these videos because they're pretty interesting and they go over this stuff in a slightly different manner, which will really help you understand. We have energy and chemistry and then enthalpy. Final slide for the presentation today, and we'll finish up the others at another time, would just to go over the abbreviations involving the letter C, capital or lowercase. So big cows and little cows are not abbreviated with just a C. Remember, they have 3-letter abbreviations. If you put the S on, that makes 4. Specific heat, however, does have an abbreviation of C. And remember, we can usually put the SSP to tell us that it's specific heat. If we just have something else that's called heat capacity, there's no specific there, which means there's no mass. That's just simply going to be a C. Celsius is abbreviated C, but it gets the little degree symbol. And the speed of light is abbreviated lowercase c. All right, so hopefully you've learned quite a bit. Feel free to Google anything you're unsure of and ask me during our next class period, because we will be finishing this up and having an awesome discussion. All right, bye-bye.